How do we make superconductors float? For this demonstration, we will need the following equipment. First, we will be using a magnet. This magnet is currently emitting a magnetic field around itself, and shortly we will be able to see how it will interact with a cryogenically cooled superconductor. To cryogenically cool, we can use liquid nitrogen, which is very cold, so we will be using gloves and tongs to handle the equipment. And of course, our superconductor. To cool our superconductor, we will place it in a petri dish and pour the liquid nitrogen on it. Because liquid nitrogen has a boiling point of about 77 Kelvin or 196 degrees Celsius, which is much lower than room temperature, we can see it boiling away at the surface. We want to cool our superconductor below a so-called critical temperature. Below this temperature, it enters what is called a superconducting or Meissner state. In this Meissner state, the superconductor can conduct electrical current with zero resistance and expel all magnetic fields from inside the material. Luckily for us, we are using a high temperature superconductor, which means that we have a high critical temperature, so we can reach the Meissner state with something as simple as liquid nitrogen. And when you put it in the presence of a magnetic field, it will float. Due to the superconductor's zero resistance, as mentioned before, as a response to the external field, when it enters the Meissner state, currents that circulate near its surface without resistance will generate and create an internal magnetic field within the superconductor. This magnetism produced by the superconductor will then oppose the external field from the magnet, causing our superconductor to float. This process is completely reversible. Once a superconductor heats up again and goes above its critical temperature, it will fall back down.
True. That is amazing.
When the superconductor is above the critical temperature, the magnetic field lines are again allowed to go through the material. So the superconductor is said to be in the normal state, where it will experience no levitation. We can now repeat the experiment with a slight adjustment. Here we will use a tactic called field cooling. Before we cooled the superconductor, then placed it on top of the magnet. This time around, we are cooling the superconductor whilst holding it in a fixed position above the magnet. Here we should mention another important detail, which is that we are using a Type 2 superconductor. Type 1 superconductors, when cooled below a critical temperature, immediately expel all magnetic lines as they switch from a normal to a Meissner state. Type 2 superconductors, however, have a third phase in between, a mixed phase. In this phase, there exist areas of non-superconducting states where the field is still able to penetrate the material, meaning that the magnetic field is not completely expelled. The sections where this field is allowed to go through the material are called flux tubes. The magnetic field gets trapped in these flux tubes, causing the superconductor to be pinned in place.
Do you want one person to hold the petri dish while the other removes it?
When we remove the spacers that are holding the superconductor above the magnet, we will see that it still levitates, but now, if we try and move it, it returns back to its original position.
Yeah, that's really pinned, isn't it?
Yeah, it worked really well.
Look at that.
Yeah, I mean, why am I wasting my time? And like, you can move it a little bit, but it does return relatively to that same position.
Because you pinned those
You can even remove the petri dish we had above the magnet, and now you can really see that the superconductor is pinned to the magnet. This can also be done with the magnet placed on top of the superconductor. As long as the superconductor is cooled in the presence of a magnetic field, you'll still see the flux pinning.
No, that is completely pinned. I'm hitting that quite hard.
Because our superconductor is pinned, we can even pick up our magnet without the superconductor falling. That is before the superconductor warms up again, goes above the critical temperature, and the magnet has to fall back down.